Alrighty folks, welcome to our next module, Module 3 in Week 2. I'm going to hop over to the site here and take a look here, and we're going to just dive right into it here. And in this module, I'm going to be giving you just a simple dive into a ray tracer, talking about some of the pieces, and essentially giving you the groundwork for the next assignment. Okay, so let's go ahead and jump into the slides, and then we'll continue. Okay, so as these slides are loading up, I'll just mention that some of these figures or formulas I'm going to be borrowing are from Peter Shirley's book, which I'll introduce later, and we'll take a look. And just for a fun warm-up, there is some interesting stuff, as I've mentioned, going on in the hardware world as far as ray tracing is concerned, and we'll take a look at that later on as the semester goes. But the keywords are NVIDIA. They're the ones sort of leading the space here at the moment. They're RTX ray tracing cards that are designed with special hardware to improve the performance of ray tracing. So while we're going to be focusing primarily on doing things in software, at least for the majority of the class, we'll try to take a look at it at the end of the semester. There's some really interesting developments going on, and again, it's why it's worth learning some of these techniques that we're going to be talking about in this course. Okay, so with that in mind, just a review of what we did last time before we move forward. But we talked about what color is, how we can see it, sort of the physics, how your eyes work, and then different types of color models that we'll then be using on the machine. So primarily the RGB A color model, why that's useful to use the additive model. So it's pretty easy to understand in a sense, and it maps well to just how we think, and it also maps well to, well, pragmatically how the hardware works with different colored LED lights. And then we talked about what a pixel is. So pixel is how we sample from an image and how we will store information. And how we do store pixels, well, in different types of image formats. We had a little bit of a discussion about that in computer graphics and how it works and how it might work at different levels, especially if we, since we're going to be generating very high quality images, want to understand what resolution we need to store images at, how many bits, and so on. And just that there's more to just the sort of PPM images that we're going to use, and that's something that we can expand on later if we like. But this gives us a good start at this PPM image format. But again, just to know that it's not the only image format that there is. Okay, and then so for your homework, go ahead and do a Git pull. You'll get your assignment from your repository, and you can continue working on that. And again, that's going to be working on a PPM image parser and just kind of getting things set up and used to, or rather setting up your framework for how you're going to develop things in this course, work with images, choose your programming language, and also describe how to run things, which is going to be important for us. Okay, so we are recording, and we'll dive into today's lecture. And today we're going to have a few key takeaways. First of all, just understanding raycasting. Second of all, doing a little bit of review of mathematics again, and then just going through the process of building a simple ray tracer. And what that's going to mean for us is, and let me bring it down in another window, is we're going to start taking a look at this ray tracing in one weekend book. These are going to be the first few books, and you're going to be surprised how fast we can get through them. They're only about 40 or so pages each with code. But looking at the first few chapters here and just talking about them a little bit more in depth in the slides, and you'll have this as a guide. And then we just want to build things. That's how we're going to sort of be learning. I'm going to, in a sense, get out of your way and let you build things as you need. I think that's actually important in this course as an instructor, to just let you guys build, but to give you some guide and talk about what some of the major pieces are here, okay? So overall, we'll want to be able to start generating scenes like this, or understand how to do that by the end of this class. You could jump into the Shirley book if you want. Again, that's this one here. You can take a look at the link or search ray tracing in one weekend. This will all be linked in your assignment, which I'll release on Friday. But overall, that's going to sort of be your assignment, sort of walking through that book, doing the implementation, and so on, okay? And again, we just want to be able to understand the intuition behind some of these ideas, so when we go to implement things, they will make sense, and we'll be able to debug them and so on. Okay, so anyway, here's our roadmap. Again, just understanding what this book is. Here's the link and some of the chapters, and really we're looking at chapters sort of 3 through 5 today, and your first assignment's really working on outputting an image, because that's going to be the first step of what we need to do. Okay, so let's go ahead and dive into it. So raycasting, one of the rendering techniques for computer graphics. And as the name implies, raycasting means that you are constructing a ray, a mathematical ray. So there's sort of a origin and then a direction where this ray is cast. You can think of it like a flashlight or a laser pointer, if you will. It's exactly sort of the same concept. And then in math, a ray is cast sort of in an infinite direction outwards, right? You might have learned this in geometry a bit ago. So here's just an example of an array here where you have your origin here, and on this Cartesian coordinate system, so there's an x-axis and a y-axis, you have your origin here at 2, 3, and then the direction where that ray is cast, and then it infinitely goes, right? And there are points along this ray where you could sample from, but this is overall the direction. So it's heading, if I look at this 2.0, 3.0, I'm adding 3.0 and 3.0 to each of it, and it's just heading that way. That's also sort of the slope here. If I take 1, 2, 3, 1, 2, 3, and put that, I can plot that point again on an array, and I can do that same experiment. 1, 2, 3, 1, 2, 3, and then I get another point on that ray. Okay, so that's the basic idea there with the rays. So again, the ray has an origin and a direction, and typically we represent it as a point. And you know how to represent this idea of the direction. Well, we actually need a mathematical concept for that, and that is called a vector, right? And this is going to get us a little bit into our linear algebra, this idea of this direction here. Okay, so let's do a little bit of vector math here. We got to talk a little bit about math, and again, I'm going to introduce it as needed in this course for the most part. And then if you need to do some review on your own, I'll provide some resources. And let me go ahead and just highlight one particular resource from today's readings, Immersive Linear Algebra. This is an interactive book, so the recommended chapters are there, but on chapter 2 on vectors is where some more material will be if you would like to take a look. And this one's pretty nice because it's interactive. You can play around with the sliders and stuff, and you know, this is a nice way to have a textbook because you can interact with the actual material. Again, it's staying out of the way and letting you play, which I really like from an educational standpoint. Anyway, so the vector basics. Well, what is a vector? It's a quantity that has a magnitude and a direction. So the magnitude is the distance or the length of this vector that we would say from its sort of starting point, which we call the tail, and then where it's heading, which is the head. So that's, we'll talk about what magnitude means and how it can be used in a few different scenarios in computer graphics here, but this is the general anatomy of a vector, okay, how it's visualized. And usually we're plotting these or thinking about plotting these on a graph like so. And again, just to be clear, here's the tail, here's the head. And again, that's important because it shows you the direction when you have the tail and the head. Okay. Just some notes in literature. You might see this in the Ray Tracing in 1 Weekend book or other resources. You'll usually see a line with an arrow over it that usually indicates, you know, this is a vector from point A to B, so it's sort of giving you the origin, the direction, right? This is the ray that's being cast, okay, so in ray casting. And then sometimes you'll see it just as a bolded variable as well, too. That's usually indicating a vector as well. So this V is actually a bolded font, just in case you see that in other mathematical literature. Okay, so again, the head of the vector indicates the direction with the arrow. So here are two vectors moving in the same direction. And if I negate each of the components, so the x and the y of the vector, I can actually flip the direction that this vector is heading, okay? Now, keep in mind here, I'm not talking about array yet. I'm just, you know, this vector here, with 3, 3 here, I can actually move this around to wherever I want, and it's the same sort of vector with the same direction here, okay? So if I just flip the x and y components, I'd have a vector heading in the opposite direction, okay? So that's to this point here where a vector can start at any location, okay? It still has the same direction, the same magnitude. These u vectors, again, the bolded u here, they all have the same length, the same magnitude. If you look at them here, they're 1, 2, 3, and then up 1 here. So 3, 1 is what this vector would be represented as. and regardless of where they're positioned, they're the same vector. Okay, so they can have any sort of start location. Okay. And here's just another way to visualize it. The immersive math book that I showed has this, again, indicating the direction that the ball is handling, is moving. And then one of those uses for the magnitude, the length here, can also be used to tell you, well, how fast is it moving? So if it's a smaller vector, one, maybe this is, it's moving in the down direction to the left. So maybe it's -1. And this looks like the length's about 4. So maybe -4 or something like that. So that's telling you that direction. Versus if I had something also moving down in this direction, say maybe just a little bit to the left, -0.25, and then just a little bit down, maybe just 0.25. Maybe it's the equivalent, but it'd be moving smaller because of the smaller magnitude. We'll talk about how to compute magnitude in a moment. Okay. Okay, so with rays and ray casting, we have some starting origin point, and they are cast in a direction, so some sort of vector here. And just to give you an idea of what this looks like, again, I'm going to be showing C++ code in this class. You can use whatever language that you like, but this is a potential representation here, where in this case, I'm creating a class. Again, if you're using something like, say, Python, maybe it doesn't make sense to model this as a class. Maybe you, or maybe you're using another language that has these built in, that's fine. But just for folks who are wondering, or if you're looking at the Shirley book, I'll try to provide some, snippets of code that I've written and so on. But anyway, this is the sort of idea of a vector class here, where I'm constructing it by default. It's just 0, 0, 0 is the vector, but I can specify the x, y, and we're going to be working in 3D, so z components here, okay, and then storing that into the class here. Okay, and then you could add whatever helper member functions you want, things like computing the magnitude or the length of the vector, and all these sort of different ideas here. Okay. Okay, so anyway, back to ray casting. So again, you're going to see sort of the pragmatic mixing in of the code here and how to actually use these. But when we perform ray casting, we have a goal. Okay, we're casting rays out into the world. Again, you can remember this like a laser pointer. And then you want to see what that laser pointer hits, okay? And when you cast a laser pointer out, if you've done this example, or if you have a flashlight, or even your phone, you could take it out and shine. You want to see what objects it hits and then light those up. Or in our case, rather, we're going to cast a ray from the origin in some direction and see if it intersects with an object. And the first object that it intersects with, say this red ball here, we would want to return a red pixel, okay, from and highlight a red pixel somewhere on our screen. So that's the idea, that's the key goal, the key takeaway, that's all we're really learning today. If you wanted to pause the video and quit the lecture because you're really pressed for time, you could do that. But that would be the idea here, not to cut myself off in the lecture, but this is the key takeaway today. Okay, so when you intersect then with an object, you'd record at what distance that intersection happened. In case the ray intersects with many objects, you take the closest object to you and retrieve the color of that object, right? We talked about color and how, a light or something would be reflected, and then color in that pixel position where the ray hit. Okay, so that's the idea here. So again, imagine you're at the origin, you shine a laser pointer in some direction, eventually a laser pointer should hit something, and you record this distance and which object or pixel got hit, and then that's ray casting. Okay, so how do I generate graphic scenes using this technique? Again, let's just kind of look at this in 2D. So maybe this is an overhead view here. This is you're the triangle, and what's in the darker gray here that you can see sort of spinning around. Sorry, it's a little bit nauseating to look at maybe. But you can see where the rays, and you have a certain field of view so you can't see behind you, okay, but you can see in the dark gray area. And you can see where those rays are being cast forward like a flashlight, and when they intersect with something like the white object or the red object, or in this case, I guess just the white objects in this visualization, the rays aren't cast back beyond that because they don't need to be. An intersection occurred there, and you know that you're intersecting with some white object here, so in your field of view there would be white in this direction, okay? So that's the idea. Here's a little bit of another visualization of this idea here. Again, you're the red circle here spinning around, and the yellow or the highlighted, this area here is where in the room you are, and you can kind of see this as as you sort of turn around here, and you're moving and just rotating. You can see the 2 blocks here. Let's just pay attention to those here. We'll see the, I guess, 2 or several blocks here. I'm not sure how many they're visualizing. It looks like just 2. They're shaded a little bit weird. But anyway, that's again the idea of what is going on. You have some sort of graphical scene that you've laid out. In this case, a bunch of cubes. You have dark cubes, white is empty space, and then you as the player. And then you cast the ray out. You have this information, this geometry, and we'll talk about that by the end, how to do spheres. And if intersections occur where those spheres are supposed to be in space, you light them up, okay? And again, that is the idea of ray casting. Okay, so let's take a look at the equation of a ray. This is going to be sort of the key here. We have to be able to cast rays. So mathematically, this is the equation. Again, one of the key ideas from this lecture, that you have some point here in 3D. T is, you can think of where this ray, again, if you want to think about your ray as a laser pointer, is traveling in time. Perhaps it's from 0 to in feet or meters or however far in front of you. That's what you are casting, and you're going to sort of sample or increment this value and check if any intersections might have occurred. Okay. So anyway, the where this point falls here, okay, your point P, and it's parameterized by T here. So where, and if you want to think about this in time or distance as the ray is cast outward, A is the ray's origin, B is the direction, so where you're shining that flashlight, and then T is the step forward that you are taking. That's your parameter. So how far along your ray has moved. So for example, here's a ray here. You could move backwards, but let's just move forward here. And at 0, you're just at your original point here, right? 0 times any direction would just be 0. And then we have A here, so the original point. And if I step 1 forward, I have my original direction plus 1 times, well, wherever my direction is. And this is some vector here, okay? Now we are multiplying a vector by a scalar here, because B here is a direction. Okay, so I've got to be a little bit clear about that. And then we're also adding a vector to this. So we want to take a little bit of look at some vector math. Maybe this again is a refresh for some folks, but it's important for us to understand again, what are vectors? There's a nice little TED Ed talk here, 4 minutes, if you want to take another look at what vectors are. But let's go ahead and look at the math operations. And here's a little cheat sheet for some of the things we're going to look at today. Well, at least a few of these ideas, and then you can just revisit this slide if you need a slide to revisit. Okay, so anyway, vectors can be added together. So here's a vector here, this blue guy, and then you have this red quantity that you're trying to add. So 2, 3, 0. And then you would add 4, 1, 0 to it and get a sum of 6, 4. So I'm just component-wise, one at a time, going 2 plus 4, 3 plus 1, and that's where I'm getting the 6 and the 4. And then 0 plus 0 gives me the third component, 0. Okay, so that's what's going on. And you can imagine this, this vector addition is just sort of sliding this other vector, because again, we can imagine them all coming from the origin, but just sliding this vector and attaching it to the end of this other vector when I'm adding them, okay? And that gives us our final point, which would be right here. Okay, so here's just another visualization of adding things together. So here's U, here's V, and if I'm adding them together, it's U here, so it sort of remains, and then V, but I'm just taking here and sliding over here to the end of U, and that gives me this point here of U plus V. Okay, so that's what I am doing. Okay, so again, why might we want to do this? I like using various gaming examples here, but here's just sort of visualizing it, and you might use vectors for things like, character jumping up and sort of seeing where they're moving, and you can sort of change their magnitude and quality in this sort of a physics example with vectors. We are going to, of course, focus on vectors primarily with casting rays, at least for now. Okay, Now, some of the physical phenomenon of, how Mario jumps and stuff, we can, maybe this is an example for something a little bit more interactive. Since we're not as interactive, again, we'll just focus on casting the rays for now. Okay, anyway, so here's the addition and subtraction of vector components. So again, just showing component-wise, and when I say component, I just mean the x's and the y's of A and B and the z's of A and B are being added or respectively subtracted if you're doing a subtraction. Okay, so subtraction works the same exact way. Again, if I have u here, I'm doing u minus v. Well, here is u, and I can just think of it, if I'm doing minus v, then I'm attaching it to the end here. If this is v and then negating it and sending it down this direction, if I was adding it, then I would just be sliding this over and we'd be somewhere up here. Okay, so that's the idea here. Okay, and here is, again, sort of addition or subtraction of your vector. And just visualizing that idea of sliding things around. Okay, so anyways, the same rules apply in 2D or 3D. Sometimes it's easier to just show you guys in 2D what's going on. But again, in 3D, the operations are exactly the same. You're just doing it with also a Z component. Okay. So a little aside here, since we're working with X, Y, and Z, and in the Cartesian coordinate system, we have to be a little bit careful with how we think of things as points versus directions. Again, a vector is a direction, but sometimes we like to think again as X, Y, and Z as a point in space. So just the different operations that we're going to do. So if we're adding two directions together, we can do that. If we're subtracting two directions, well, that gives us another direction. A point plus a direction gives us a new sort of point in space. A point minus another point gives us a direction, but we can't really add points together. Again, just if we think about it mathematically, it doesn't really make sense because, if you have two tennis balls with you, for example, what would it mean if you added, a point and a point together? Would they combine? What would happen? It just sort of doesn't really make sense. But if you're subtracting the quantity between 2 points, that would give you a direction from, one tennis ball to the other one or whatever. Or if you throw a tennis ball, that gives you, well, where your point is and then the direction that you're throwing it. Okay, so point plus a point doesn't really make sense to add that quantity. It doesn't give you anything new. There's nothing to really derive from it. Okay. Okay, now, so those are subtraction and addition. So we have to talk about multiplication, and this is by a scalar. That means we're sort of lengthening the vector. So remember, a vector has a magnitude and a direction. And again, if you want to think about a baseball, football, bowling ball, whatever, and throwing it at twice the effort, that would be sort of scaling it by k. That would make it go twice as far if you threw it with twice the effort. Okay, but it's still going in the same direction. So again, the scalar, if you're going to scale it, you have some scalar s, you multiply it by each of the components, okay? And it, in effect, lengthens that vector. So here's multiplying by 2. You can see you're just adding the vector twice, if you want to think about it that way, to each of the tails, or 3 times, again, as in this example, okay, with a little animation. Now, you don't always have to multiply by a scalar to each of the components in an equal way. Again, this might be used, but a uniform scalar is more frequently used, but just in case you see the notation of a x between the scalar and the vector that you're multiplying, this might mean you're doing something non-uniform, only 2 of the values by the scalar, and then the third one's different, or something of that nature, okay? So occasionally you might see that. Okay, and then we talked about the magnitude of a vector. That's the length. So computing the magnitude of a vector, again, gives you its length. How do you get that? Well, you take the square root of each of the components. So a, the x component squared, the y component squared, and the z component squared, and that gives you the length. So when you see the bars next to a vector, that's the thing bolded here, that's giving you the length or the magnitude, okay? Okay, and a nice property once you can compute the magnitude, and again, we'll talk about this or introduce it again as we sort of use it or need it is that you can make a vector what is called a unit vector. So you have your original vector here. U is just usually the notation used for unit vector. You take the vector and divide it by the magnitude, which we just computed, the length of the vector, and that, in a sense, normalizes it. That means that the vector will fit within the unit circle. We typically like doing this because it means if we have a unit vector, everything's sort of normalized. We know what the range is. Everything's going to be between 0 and 1. It makes our units more consistent. So this is one of the reasons that we use unit vectors, okay? The direction stays the same, but everything is, in a sense, normalized here. And again, this is important because usually we're making an assumption that things are within a certain range, like 0 and 1. And if you get outside of that range, you might not be scaling two particular quantities properly. So an example of this, we just learned about color, and I said there's a range between 0 and 255. Well, what if you had the range between 0 and 7,000 or some huge quantity? You would need to normalize whatever that intensity value is. So it falls between a range of 0 and 255, okay, so that it has some meaning. Okay, so we often do that with vectors to make sure that they're within this range. Okay. And again, notation-wise, sometimes you'll see the U. Sometimes you'll just see it as a U, and that might mean it's a unit vector in itself, but usually you'll see it with this little hat on it. Sometimes it's pronounced U hat, and that means you have a unit vector. Okay. So again, it's normalized is what we said. Okay, just to make sure that we're working with quantities that are all normalized together. That means they're all sort of in a consistent form. And if you need to scale things later, you can always do that by just multiplying the vector by some scalar k, as we've talked about. Okay, so again, just practical usage. Here's a little game here, Worms Armageddon. You're going to see at the start of this animation where you're sort of aiming where to fire the projectile. So you're just sort of looking up, down, and you don't want to have any sort of length or magnitude associated with the vector. You're just sort of aiming. That's the player's goal, not to choose the distance like you would, say, a slingshot based off of how far you pull back the slingshot, but instead you're just picking a direction and it's normalized, so it's consistent behavior no matter where you're targeting here. Okay, so then again, here's just another cheat sheet for you with a summary of some vectors and their mathematical properties. Okay, so I'll be sure to, I'll move this to the cheat sheet that I showed earlier on slide 31. Okay, so here is an example vector class. I actually borrowed this from the Peter Shirley book. You're welcome to use this or build your own because math is going to be an important part of this class, or at least how to utilize these operations, to sort of have your own toolbox to do these different things. Okay. Okay, so now that we understand a little bit about the math here, we can return to our goal of ray casting. Okay, we at least know what the primitives are, and we have some, intuition about, well, how do I use the code? And I think, even though this is C++, let me still give a little bit of a overview of what's going on. You saw my sort of example here where we had the construct the vec3 already. You could call this ray if you wanted, whatever. We're just going to model it as a vector. Here's a constructor here with an x, y, and z component. Shirley refers to them as element 0, 1, and 2. They're probably better labeled as x, y, and z. And those are stored in a array that holds exactly 3 elements. They're all doubles, so you get pretty good precision there. We've talked about why that might be important. He's supporting the different operations like subtraction, accessing with the brackets, doing addition, multiplication, and division. Okay. And if you have any questions ever about this kind of code and how to translate it to your particular language, once we start doing assignments, I'm happy to help you there. Okay, so anyway, let's continue on. So again, provided in the class, now that we have a vector class, we can build this ray class, So we know ray has two things. It has an origin and a direction. Okay, so the point and the vec. And a note to make here is that the point3, this could be a separate class, or sometimes people just use a vec3 as well, with the understanding that it doesn't have all these properties. They really just want something that holds an x, y, and a z, and they don't want to mess around as much with, in the actual languages, the type systems to support a point times a vector and all these sort of operations. But realistically, you probably do want to actually do that just to make sure you never add 2 points together, for example. But anyway, a little bit of a digression here, but so this is the array class and how it's set up. Well, what's the important part here? This at function here. We're saying, okay, the point3, so where am I along my array at, well, wherever t is, and that's the origin plus t times direction, okay? And let me rewind a little bit just to put this fresh in your memory. And you can open this in another window if you want, but here is where we're looking at t, our origin plus the point t times some direction, okay? In fact, let me just copy and paste that into that slide for you. Okay, so now here it is magically, by the powers of video editing, this little function here. And I can just rename p at here because you're finding the point at some location. Okay. Okay, so we at least have this idea of, you could create an array, or excuse me, a ray, R-A-Y, with an origin and then the direction here that would be stored here in this constructor. And then you'd be able to figure out, just using this formula where some point is t according to this ray. Where is it traveling along? Okay. This is a little bit on C++ stuff, so I'm going to skip this. This is a little bit of an aside, but if you just have, again, questions about parsing C++, happy to help you. Okay, and again, here's our goal, though, what we're really trying to do, the raycasting in 3D. We have some point here, that's you here. Imagine yourself spinning around and, I don't know, this is a fun house or something, and just kind of looking around. And you're casting, you only have a flashlight where you can see. This would be a little bit scary, but the stuff that you can see that's being lit up by the rays is, again, where you plot cubes. And you're plotting cubes, you can imagine them as cubes and little pixels that make up each of these cubes everywhere that your light shines and lights up one of those cubes, okay? And you're only lighting up the closest thing, nothing behind it, because you can't see behind or through something, although we will have to talk about transparency at some point, but this is the idea. And this actually, again, goes back, that raycasting is really quite an old technique. Old games like Doom and Wolfenstein, if you've ever taken a look at those, use this technique. And this is how basic 3D games were actually created back in the day. And then we're going to push this further by rendering stuff that looks nicer than this. Okay, so anyway, we can use this ray casting technique to draw a 3D scene by casting many rays, okay? So we're going to start off with spheres, but our geometry can really be anything. We can, do cubes, triangles, pyramids, 3D figures, again, like you see in Pixar films and so on. This is the idea here, okay? So anyway, what we're doing here, or what to sort of understand, and I'll maybe talk about this first image here, is we are, from our origin, we're just casting a ray out into each of our pixels on our screen. So one of these rays is sent out, and it hits up, and if it lights, or rather if there's an intersection here, it's going to light up that pixel that it traveled through to get to this object. And it's going to say, hey, this object's green, so I'm going to light up the pixel green, okay? So that's the idea of casting rays and performing this ray casting technique. So per pixel, you're going to cast out one ray. If it hits an object or intersects with it, and we'll figure out how to do that mathematically, then color in that pixel on the screen. So it sounds pretty simple in a way. It's sort of intuitive, okay? And on the visualization on the right, we're casting rays from our origin to our object, again, in these pixels. You can see they're just sort of scanning one at a time, so you can imagine doing this in a loop for all of these individual objects. So both of these images are showing the same thing, okay? And based off of your resolution of your monitor, you get some estimation or approximation of what this shape looks like. So here, if you only have a few pixels here, this is a 5 by 5 resolution monitor. Very small, but you can still see that there is some sort of circular shape here. Okay. Okay, so here's just a second visualization where rays are being, again, cast from some origin and hitting an object. Maybe you have multiple objects and so on, but we're only really highlighting the first object that we see here. Okay, so here's our virtual viewport, in other words, our eye into the world. Our virtual screen, this is the window or a window size, whatever the resolution is, if it's your full screen or maybe it's just a 400 by 400 window. And then the objects that are visible, okay? And we're going to talk about, or have to talk about, things like perspective and some of these things in a little bit more detail later for how we create the scene, okay? Okay, now something else important to keep in mind and why ray casting is a really powerful technique is your ray could actually hit this object, and this one's kind of cylindrical, but depending on the material, it could actually bounce around multiple times. Okay, and that's a really important idea with ray casting. That's actually why it's a very powerful technique. I'm going to contrast this with rasterization and sort of a more traditional technique in a moment, just in sort of a summary slide, but the idea is if this material was curved or maybe it was glass or something that, you know, the ray could actually travel through, it could actually bounce around multiple times. And that's how you get reflections in the real world when you think about light bouncing around and interacting with objects. Okay, so that's a really important idea that rays can bounce multiple times. So here's just sort of the, again, power of ray casting here. Here's my origin at the middle, and you can see where I'm sort of aiming it. And along this white line here, you can see where the path that the ray takes, and it sort of bounces around and hits these multiple objects here, okay? And depending on the properties of this object here, if it bounces and then hits this object, it might light it up or so on, okay? So we'll figure out ways of, you know, how that is done. Okay, just another little aside. So again, when we think about rays, and we talked a little bit about electromagnetic you know, radiations, that is light, and how that travels as a wave. Sound is another wave. So for those of you who are into music or sound, you know, it's not graphics related, but you can also think about modeling sound as it travels through a 3D environment, okay? If you're really getting into music or designing an auditorium, a theater, an amphitheater, whatever, you would probably think about these things and consult with someone who's going to think about, well, how's the sound going to travel? Is it going to bounce all over the place? Next time you go to a movie theater, you can think about this. Think about how you have these big speakers, how they might, the sound might bounce around from the speakers, and why the walls are covered often in carpet and the ceilings, okay? So just a little aside there, in somebody's paper if you want to learn or think about this problem a little bit more. Okay, so I haven't really given a fair contrast with the pros and cons of rasterization. This is sort of the old technique for graphics, or rather for real-time graphics use something called rasterization. And we're talking about rays and ray casting in this course. So in rasterization, you used to say, okay, for each object in your scene, you know where all the objects are, which pixel is closer, and you draw that. Ray tracing, you're going one pixel at a time, casting out these rays and seeing what it intersects with, okay? And then you can sort of bounce around those rays and do these other kind of cool techniques here, okay? So which is better? Well, I don't know what you mean by better. That's something we have to think about, because you'll see that both of these scenes here, whether using rasterization or ray tracing, you can draw the same image typically. Okay, there's just different means to get to it. But historically, there are just some trade-offs with what we're talking about in this class using ray tracing, meaning we can often get more realistic materials and the kind of things just because, well, one, we're doing things at non-interactive, so we don't have to do it at 60 frames per second. So there is some performance that we don't have to worry about. And since we're modeling how rays sort of travel in the world and sort of simulating physical properties, we can often get physically based materials modeled much more accurately, and they sort of look better in a sense, okay? So again, there are different ways to achieve a different scene, but of course we're talking about ray tracing in this course, okay? All right, so we've been going for a while, so if you need a little break, go ahead and take a break, and then I'm going to jump a little bit more into implementation stuff in the Shirley text. Okay, folks, so hopefully you gave yourself a little bit of a break, and if you're joining us, I want to just start preparing you for the next homework, what you're going to be doing. Again, we're going to be looking through Ray Tracing One Weekend, the first book, if you can believe it, and implementing this. Again, it's a free book, and you're technically building a path tracer, this idea of casting arrays and sort of following them. But you'll be able to generate this image here. So in about a week or so, you'll have this nice, beautiful image, and then have some idea of how to build these tools and how powerful this technique is. Okay. So how are we going to build our ray tracer? Again, well, we're not going to use any graphics APIs. We're building this from scratch, right? Just like you're doing for assignment 1 for your image loaders. And again, you can use any programming language you like. If you want to switch, you can. You'll probably figure out after assignment 1 if you like the language that you're working in. You're going to need to output an image. You'll know how to do PPM images. And I'll also just, let me see if I can find the Shirley text in one of my windows here. If you do need help, there is a little bit on PPM image format in the first chapter, or excuse me, second chapter of the book. So feel free to take a peek at that. Okay, and you'll be able to just display those PPM images, right? Because we need to draw into something. Okay, so some code examples. Well, here's just an example of drawing PPMs. Again, this is sort of the helper function provided with the Shirley book, but you're going to need some way to draw some sort of image and output a P3 and then write out all the pixels. You're just sort of iterating through all the pixels here. You're going to output some sort of file here, open that file up, figure out what the dimensions are of your window. I'll talk about that in a moment, and then output, hey, this is a P3 file. It's X by Y. The range is 0 to 255, and then write out all those pixels. Okay, again, this is what you're working on, or maybe finishing up for your assignment 1 by the next module. You're probably going to need some sort of math library. Since we're all using different languages, typically it can be a fun thing to implement these from scratch, but you're welcome to use either, again, building off of Shirley here. He's got a class example for C and C++ folks, but JavaScript has, a math.js or GLM-JS library. Python has NumPy, whatever the language you're using probably has a good matrix or vector library that you can use. I'll try to provide suggestions, but if I've forgotten, they are, here's a few in this slide. So you're going to be able to, you're going to need some way to model a vector or be willing to build it yourself, which is actually a really good exercise to have that control. Okay. So let's talk briefly just a little bit about the scene setup, just recalling that, we can look at this sort of image, and this is how we want to sort of structurally how we're going to, create our program here. There's a few, four main components that we want here, right? We have the objects that we want to see, so we need to model them in some sort of way. If we're doing this in sort of an object-oriented manner, this is one way that we can model things. We need some sort of window or a notion of a window, right? What's our boundaries here? And then we'll have certain properties of it, like the field of view and some of these sort of things. A viewpoint, meaning where is our camera? Where are we viewing the scene from? This is you in the world. And then the rays that we want to cast from our viewpoint into our world. Okay, so let's just take a look at some of these things with a few ideas about how to set them up, right? So we're going to need some sort of window here and some coordinate system. Okay, so so we're going to use some sort of Cartesian system, and I would recommend sort of following what Peter Shirley uses in the book. You can use anything for what you want, but typically we have an X, Y, and Z, where X sort of points to the right in the positive direction, Y up, and then positive Z is towards you. So I would recommend just keeping this consistent with whatever Peter Shirley does. I'll talk a little bit more about this maybe next lecture and for sort of structuring this, but you can sort of just set this up using different vectors. So you say, all right, what's the lower left corner? What's horizontally, how wide is this? So if my bottom left corner is -2, -1, 1, in my horizontal, my width is 4, xy, that would put another point here, 2, -1, -1. And then my vertical would be, well, 2 here, so I'm going 2 up in this direction here. And that sort of gives me a center here, so I can sort of move along from -2 to 2, and then from -1 to 1 here in the up direction. So this is sort of a 4x2 window, if you want to think about it that way. You can, again, scale these dimensions however you want. I believe this is what Shirley does in his book, so I'm just trying to match what he has here. Okay. And then, as mentioned, we need some way to cast rays. So we've looked at a ray class previously, but you might use it with some math library here. So here I have GLM Vec 3s here. You know, so you can use this class or you can model your own. I don't really care. Whichever you decide is fine. But you do need some sort of ray cast functionality. Okay, so where you have a data structure that has an origin, and you can just model it as A and then a direction B, or you can call this origin and direction. Those are probably better names for it. And then usually it's helpful if you're doing this in an object-oriented way to be able to get the origin and the direction. If you're not using an object-oriented language, that's fine, but just sort of try to keep in mind or maybe name these things nicely. So you can either name them A and B because that matches the math formula, and then I would put a comment here what A and B are, or just name them origin and direction, and then also put a comment about you know what this is constructing. Okay, and again, the goal of this is this point at parameter function, or the at t or the p of t function here. And I'm using floats here, so maybe shame on me, but maybe we could use double or something. But this is where we're going to test if there is some intersection. Okay, so again, this is just this formula here, point at parameter, that we've looked at here. So where, when we cast this ray from its origin to the direction, where is it? Okay. Okay, now we want to draw some things though. Okay, so we have some rays. We want to sort of send them into the screen and see if they intersect with, well, say a giant red sphere here. I can't tell it's a sphere. It appears as a circle. We'll talk about adding depth and so on. But this is the idea here. Okay, so how do we draw this? Well, for now, when we draw figures, we're just going to have to mathematically model them. So, this means understanding just a little bit about the equation of a sphere here. So spheres have a radius r and then x, y, and z coordinates for its origin. Okay. And if where we're drawing the sphere isn't exactly at the origin, then we need to offset it by x here. Okay. Okay, or rather, excuse me, the c of x here, where c is the center x position as well as for center y, center z. So if the sphere is in the origin, we don't really have to do any work here. But otherwise, we can model in this way. And I haven't mentioned it in this lecture, but the dot product is how we can actually compute if we actually want to do the point minus the center here, and then do the point minus the center here. Okay, so just multiplying these two components. So a point of where our sphere is, or how to model it, and then the center position here. We can compute that with dot product, or we can just use this whole big equation here. That's fine. Shirley uses this little trick. That's why I'm just noting it. Dot product is just a component-wise, well, it's a few things, but how to actually use it is multiplying the x's of this point and the x's of the center by each other. Okay, so again, it's just what's shown in this equation. Okay. So anyway, a reminder of our goal is to draw a sphere for any point P that satisfies this equation here. Okay, meaning so if I have some point here, some point at T here, that's what I'm trying to draw, and then my circle here, okay. And if I sort of expand this out, so this is just using the little dot product T. So what's P of T? Well, that's our ray that we're casting here. That's the A plus T times B, and then minus C here. I'm doing that twice. And then you sort of move all the items or the terms to the left-hand side. So this R times R moves over here. So it's going to be minus, and then if it equals 0. Okay, so what does that mean here? this big equation. And Shirley does a nice job explaining it, but again, I want to give you some intuition here. But if we're saying some point at t that we're multiplying through here, if it satisfies this equation, if we're solving for 0 here, then there's no intersections that occur. Okay, so I take this computation here, okay, that I do here. And then, again, when I solve for it, what I'm really solving for is how many times when I cast a ray here, is there a point at t that goes through this sphere? If there's at least one, maybe on the very edge, it just skims by, that means there's sort of one root here. One, and by one root, I mean one thing that satisfies this equation. If there's two, then it intersects twice, right? It goes through an object. Again, pretend you have a laser that can go through an object. Then you take the smallest or the closest of those roots, and that tells you where that intersection was. And then if this is a red sphere, you color that pixel red. Otherwise, you just color it whatever the background is. Okay, so I'm going to leave this little algebra reminder for you on just sort of solving the equation and sort of finding the discriminant, but it's just a little algebra refresher. The Shirley text does a nice job here, but what we're really doing is computing a ray sphere intersection here. So let me actually maybe put a note here. I'll put it on this slide here. Implement a ray object, compute a ray sphere intersection. See previous slides. And then you want to be able to draw this actual sphere here, maybe just in the center or off of center, just to see that it's working. Okay, so that's the main idea. Okay, or that would be a good checkpoint at this point to know that you can output some pixels, generate a sphere, and then cast some rays through, testing every pixel here from the corner all the way over, just one row at a time, and seeing if it satisfies that equation. If it does, you just say, hey, I'll make that pixel red. Just pick a fixed color. Okay, we'll worry about modeling these objects in a moment. So that's going to be sort of the first goal of the assignment. Okay, common gotchas for this, right? Since you're generating images, you have to rerun your program every time you make a change and regenerate a new image. Okay, now the second step to your ray tracer, or where I would say is going to be a good step for us in assignment 1, I'm going to talk about the next things that'll be sort of interesting, is say, okay, cool, that we can draw this sphere, but again, our sphere is looking relatively flat, right? It's just a red shape here. So what are we going to do here? Well, first things first, we also need a camera too, because we have to figure out where we're casting our rays from, our origin here. We might want to move that around different places. So we can sort of embed, as part of our camera, how big our window is. That's this guy here, how many pixels we have in our sort of virtual window here. That is, how big is our PPM image? That's what I mean by virtual window here. And then, our origin, where the camera is, and where it's the direction that it's casting rays out to. Okay, so this is essentially, you might have a function here. This is what Shirley does in text. He has a getRay function here that casts out a ray from the origin out to the window to each of the different pixels here. Okay, so then, again, it's also probably useful, or going to be useful, to have an abstraction for the spheres, where you have the center and the radius of that sphere, just to make your life a little bit easier. Again, you can see I'm really leaning on object-oriented stuff, but you can do this without objects. You can just have a, if you're using Python, you could just have a list that has a sphere and certain properties and so on. There's many ways to do this. Or if you're using Python, you can just create objects in a class anyway and kind of model off of this. Okay, so anyway, here's the sort of hitting the sphere part, right? So this ray sphere intersection portion here that I discussed here. So here's sort of your A, B, and C, and you're solving this equation for this discriminant and testing if there are any intersections. Okay, if there was an intersection, you want to return where that nearest intersection occurred. So you know when you hit some object, how close is it? What is that object, and what's the color? Okay. So in this C++ code here, I have a sphere. I'm casting a ray into it and solving this equation to see if this ray that I'm casting actually intersects with this object, right? I'm solving to see if there is some intersection, 0, 1, or 2 intersections that occur here. Okay, so you'll have sort of this to do creating some spheres and however you want to model this. In my case, again, I'm just creating a bunch of spheres here. I'll have maybe a scene that I can add some objects to and then just iterate through them. And then every time I cast a ray, just check and say, hey, did I intersect with one of those objects? Okay, that would be the idea. Okay, we'll talk about making things more efficient and so on, but that's the idea. Okay. Okay, so anyway, we're still trying to get to this point where I said, well, hey, our scene's looking relatively flat, so how can we fix that? All right, so then, we'll have more spheres. We can do this sort of abstraction here, but, how can I make this look a little bit nicer? Okay, well, here's a little bit of the scene abstraction here where you can just add some objects and so on. Just have a vector of those objects that you send them through. Maybe your scene has a background color as well. These are just some of the little touches here that I'm adding in my code, some things that you're going to have to think about here. Okay. Okay, so here, let me just kind of get into this portion here of our scene, again, of just showing how I'm iterating through each of the objects one at a time and then just testing them for, well, all of my objects in this case are spheres. I'm just checking if they're hit. Again, we can talk about building abstractions of different collision when we have non-spheres. We'll eventually have to get into that. But anyway, just to see if our ray intersected or collided with some other object, okay? And if there is a hit, then we output the object's color here. So t greater than 0.0, okay? So that was, again, testing where our intersection occurred. So if I cast a ray out into space and it hits and returns some distance because there's an intersection, t must be greater than 0, right, from our ray. So it's in a sense giving us the distance that collision occurred at, okay? And now what's going on with this work here is, well, it's just saying, well, there's a little computation that we have to do here with the normals. Okay, so how do I get the illusion of depth? Because again, I've modeled my scene, and again raising this issue of how do I make my sphere look like a sphere and give it some depth? Okay, well, we need the normal of a sphere. So normal might be a new concept for some people, depending on, not everybody took graphics, but the idea is if I look at this sphere here, it kind of looks like a hedgehog or a porcupine, right? It's got these little sticks out of it. But if you look carefully at it, each of these little sticks that are poking out are the normal of these squares here, or these quadrilaterals. They're not quite squares, but they're quadrilaterals, so some sort of rectangle. And the normal is perpendicular, so that means it's sticking out. It's 90 degrees out of each of these planes. That's what the normal is, okay? And these normals, if I look at them, they're sort of pointing in a direction, right? The ones that are in front of me are pointing straight towards me. The ones on the side are pointing to the left side. And that gives me an indication of the direction, right? Where these little points, again, if you want to think of this as a hedgehog or a porcupine, are sticking out. Okay, and that tells me if I'm looking at this scene straight on here, the difference or the angle at which I am, looking at this. So I'm looking at it straight on, so this thing's pointing straight at me. That's some sort of information that I can use. So from this, again, and let's use not just porcupine that's sort of sticking out, but these are vectors that are sticking out, right? They have some sort of magnitude and direction, so they're all normalized, so they're all pointing out, they're unit vectors here, representing a normal that's sticking out. And what I can actually do here is, well, this is what I'm saying here. We can get the normal by subtracting the point of intersection by the center of our circle. So where I intersected with this circle here, okay, and I subtract the point of that intersection, then I can generate this sort of normal here. And what I can do with this normal, and perhaps it's easy to, again, just show this in the code here, the normal, so it's a vector here. So I say, okay, the ray that we are casting here at some point t minus the object center gives us this normal, okay? And once I have that normal, well, I have to sort of normalize it here. I have to put it in within a range of 0 to 1. That's what this little trick is doing here, okay? And then once I've imputed that normal, which I've done here, that's this line, then I'm going to multiply times equal by the red here. So something that's directly sticking out at me that I'm multiplying through this normal is going to be very red, versus something that's on the corner, it's going to actually build this little sort of shadow because it's not pointing directly at me. So again, if you imagine this is a flashlight, and I'm pointing it directly on the sphere. Let me go back to the sphere image here. You know, you can start to see some depth here on this corner of the sphere. It depends where my light source is. It's actually, or where I'm looking, this probably from this direction, because this side's brighter. But this side should be shaded less here. Or maybe my light's a little bit on the corner here. But you can see that this looks a little bit more 3D, okay? So that's the idea here. Okay, that's the main idea. Okay, now there are some tricks for computing depth. Again, students who took graphics with me might recall this Z buffer, but the idea is if I have multiple objects, it's the same here in ray tracing, casting a ray out into my scene through my window, I want to take the object that I intersect with first. That's what I care about, right? A is in front of B, which is in front of C. So A is our first object, so it has the smallest distance, that T value. That's what I want to actually draw here, whatever its color is. So maybe these triangles are different shades here, which you can tell. So I want to shade it whatever A's shade is. Okay, so that's the idea here. So that's what this closest T is, okay? Whatever the closest T is, that's the color that I want. Okay? So your objectives at this point, in sort of part 2 of what the assignment will be, is to then be able to compute those normals for your spheres, have some sort of order, have some color to the spheres so you can see the different colors, maybe create a scene with a few spheres, and then maybe you can try moving around the camera and so on. Okay, so you'll get something maybe that looks like this here. Okay, and then just a little bit more. Step 3. Is getting a proper field of view, because things are looking a little bit squished here, okay? I haven't taught you how to do an ellipse yet, but things are squished, okay? So when we look at things in the world, we want a sort of perspective view, and maybe I'll talk about this a little bit more to figure out, why this thing's squished here. But in order to fix the sort of squished sphere that we have to edit the camera. If you've ever done some photography, or maybe you've had a GoPro, you've put on a fisheye lens, or these things that sort of distort the image. So we have to make sure that we're sort of viewing things such that when they're farther away, or when they're sort of towards the center, they still render in a perspective, or at least something that's reasonable to what we see in the real world. So maybe a field of view about 45 degrees. Okay, so the field of view is how wide we can see, if you want to think about it that way. Right, an owl or perhaps some sea creature has a very wide field of view, very wide peripheral vision, and thus that makes them better hunters, perhaps than us humans. Owls can also hear, a mouse's heartbeat from, hundreds of feet in the sky, but just their or maybe owls aren't the best example, but other animals might have a larger field of view than humans. So we want to model it somewhat reasonably here. And what I'm showing here, I'm going to show a lot of ideas, and we're going to reiterate them again many times, but this is the view frustum here, where you have your camera, your field of view, so how wide this triangle is going to be, how near objects are that you can see, and how far away objects are that you can see in your scene, right? So it's just like your human vision. You have a blind spot in front of you that you can't see things that are too close, and then you can't see things that are a million miles away, right? So you have some distance. So whatever falls within this portion of the view frustum that I'm going to highlight here, these are the boundaries, this guy here, that's what you'll be able to see. And then with a particular field of view here. Okay, so this is usually called the half height, which is some angle, that's your field of view divided by 2. Okay. Okay, so this is, again, going to give us some sort of aspect or perspective, I should say, okay? And our window itself is 800 by 400 pixels, or a 2:1 aspect ratio, right? We had this sort of 4:2 thing, and then we can arbitrarily choose how many pixels there are. Okay, so we're almost there at this point. We've got some view frustum here, and we just need to sort of multiply our camera here to figure out the orientation, or to orient this view frustum here, okay? So that when we're casting our rays, we're casting them out not directly, but they're almost coming in at an angle here in our scenes, and that's what gives us the perspective view, and they're being sort of shot out at an angle. And you can sort of see that along the edges. If you follow along the edges, they're not being viewed sort of orthogonally, okay? I'll do another recap on that in the next module, okay? Okay, so that's where I want to stop today, though, because that's a lot, and we need to recap a few other things like normals, the camera that I was explaining a little bit, but that'll give you an idea of what you're going to build, some of the components of a simple ray tracer, and you could get some scene like this by about chapter 5 in that book, and by chapter 5, I really mean that's like about 20 pages of reading. So you can actually generate something really quickly, but we'll want to, again, sort of understand these things a little bit more in depth, just to, because we're going to build on this in the course, okay? So that's the idea. You'll have a little in-class activity that should be ready for you to go. And we'll pick up, and then this first assignment will be ready for you to knock out. Essentially, you'll be going through the ray tracing in one weekend book, so you're welcome to get a head start of that, but that'll be available on Friday. So we'll see you then.